Okay, and this is a stereo pair. Okay, this is a data set that's standard. It's called a Middlebury data set, and this is supposed to be a stereo pair. So the stereo pair means that the camera was actually, there was a translation. Okay, like I told you, only if there is a okay, not the lower one. Okay, so only if there is a translation, you can get a parallax effect. And as we know, right, the objects in the front will tend to move more, objects in the back will tend to move less, and therefore, right, that gives you a cue for depth. Only thing that happens is the camera translates, and on the right hand side is really a reconstructed sort of a depth map, which looks pretty. I mean, it may not be that fine to the level that you want. For example, you may say, I'm not able to see his nose completely, right? This looks like the whole thing has come out as one thing. So it depends. It depends on for what application you want. Okay, this is stereo. So here the camera actually translates. Now if you observe, right, this one, the earlier one and the earlier one. So the first one was shape from shading, next one was photometric stereo, this is the third one stereo, right? So in all of this, what we are following is really a pinhole model, right? A pinhole, because none of these was blurred, right? Did you observe that none of these images were blurred? Only the illumination was changing, and some shading was going on, but we never had blur in them, which means that these are all assuming a pinhole model, or they're assuming that you are capturing with a lens that has a depth of field large enough so that you don't see any blurring effect at all. Now the next one, right, is something that is called a depth from defocus. So what this means is that you take one image with again here the camera is not shifted. So the idea is that, right, each method has its own set of strengths and as well as weaknesses. So stereo, the weakness is that when you kind of move the camera, now you have to look for feature correspondence. Right? You have to know where each pixel is gone, and that is what gives you a cue for depth. So in that sense, that is what makes it hard. Especially, right, if you have patterns that actually repeat, in which case when you do a correlation, you could get kind of confused whether this point moved there or it moved, right, I mean, next to it, because it could be a repetitive pattern, or it could be that you have such a smooth region that it's hard to tell, unless you have a feature, it's very hard to tell, right, where to match it. So for example, if I tell you that from here to here match, how will you match, right? Is it not? Because they all look the same. So if you have features, then it's easy. If you don't have features, then it's hard to tell where a point is going. So stereo also has its issues. Another thing is occlusions. So okay, that is something that we don't have to talk about now. But so similarly, right, when you come to this one, a defocus thing, depth from defocus. So here what is done is you take a picture with a lens, with a real aperture camera, and then assume that there is a depth of field, right, which is in action, in the sense that you get varying levels of blur in the image, and you know that, right. Suppose I ask you, I give you one image which has a space variant blur. Let's say, right, that this class, suppose I take a camera, I focus with respect to the front row. Okay, it's in my hands, no, what I focus with respect to what kind of working distance. I focus with respect to the front row, all of you are blurred. Or let's say I focus with respect to middle row, the guys at the back are blurred, the guys at the front are blurred. Can you use that one image and tell depth? Or can you devise an algorithm? As a human being, you will do all of that, but let's say, what would you do? I mean, if you had to do it, can you devise a method that will use a single image and be able to tell? It is hard, no? Why is it hard? Because of the fact that, see, you may think that if I have some way to find out, okay, if something is more sharp as compared to something else, right, you could still go wrong because of the fact that, right, see, it can happen that in an image, okay, you find that, right, some region looks like it is actually blurred, but then that would mean that you'll have to evaluate some kind of a sharpness. You should have something like a sharpness, this one, right? You should have some operator that will tell you the degree of sharpness. Let's say I have some sort of a tool like that, which if I apply on this image, right, it will actually tell me what level of sharpness is there at let's say every location. But if at some location, if I say this operator tells me that this has more sharpness as compared to something else which has less sharpness, it doesn't automatically mean that the one that is more sharp, right, is actually in focus. Okay, it could very well be that this guy is actually more blurred than the other, and all the sharpness is coming out because of the fact that the intensities below are much more active here as compared to what is happening there. You see that, right? So I could end up interpreting things wrongly just by having one single image, unless you know that it's all uniformly textured, the whole scene has the same texture everywhere, then it is okay. Okay, then because the underlying uncertainty about what the image might contain is gone, because right, they're all affected by the same image intensities, then it is okay. But then that's not the case normally, right? You have intensities varying all over, like me, then this background, right? So you can't, so you have to worry about what probably the underlying intensity was like, and that could affect what your focus measure is telling. Okay, and therefore with a single image it's hard to tell. But then if I have two or more, okay, then it looks like relative notion comes in now. Okay, because in depth from defocus what happens is you take one image and then you change the lens parameters, you stay right there, you don't move the camera, you take one more. And now the idea is that some places would have become less blurred, more blurred, and that would now start to act as a cue, because now relative, but because now the the scene is out of the way, because you have that both are affected by the same underlying scene, no, because you have not moved the camera, and now you know that if there is a change in blur, probably that could act as a cue. Correct, because the underlying scene is will no longer influence your idea about what is the degree of blur. Okay, that is what is depth from defocus. So this, in fact, right, I mean things like this, and I recently read there is a Panasonic, which one, Lumix GH5 or something, that 2019 they used this principle in order to do this hunting. So hunting is when you want to do an autofocus, no? So autofocus when a camera does. Okay, one of the things, by the way, it uses this sharpness measure. Right? It will capture a bunch of frames quickly. We don't see any of that. Okay, we just see the final picture that looks nice. But then it captures very quickly a bunch of frames, and by sort of moving the lens. Okay, it doesn't worry about scaling and all that, because all that it needs to know is where are things coming into focus, especially with respect to the central region. So it runs a focus measure, as it is called, a sharpness measure quickly. But this Panasonic thing, that is what all other phones do. They capture something like 30-40 frames and then quickly run a measure, because relatively you know where things are coming into focus, and then you kind of freeze those lens settings. But this guy, Red, apparently has run up 100x speed on that, because he just uses two images and then it computes, gets an idea roughly about where the object is, and then does a bunch of frames around that. So now he doesn't capture 50 and all. Just captures probably 10 frames around the place where he senses that that is where the object is, and then does something very very fast on those few frames. So this is something that I just read somewhere. Okay, so I was trying to see where these people use this depth from defocus and all that. So hunting is one thing, right, where they actually use for autofocus. But there, really you're not interested in finding the depth map and all that. You're just interested in knowing how to use blur as a cue to know where you want to focus. Okay. Now, depth from defocus is this, and then further going down, okay, this is this shape from focus, right? It's a ring, okay, it's a ring, okay, and what is being done is there's a microscope, and that microscope, so it has a stage, right? You keep the ring on the stage, and then you move the stage up and down. As you move the stage up and down, right? So similar to what we have already said, right? So basically different layers will come into focus, right? So there will be, so as you can see, right, not a single frame will be completely in focus. See, here the face is blurred, the background was sharp initially, then later the face became sharp, the background became blurred, right? So if I play it again, just watch, right? So basically nowhere, right, there was no single frame where you could have said that the whole thing is in focus. And this you are talking about a ring, by the way, right? So you can imagine the depth variation is hardly, a few millimeters. That's all you can engrave, right, on a ring. But the blur is showing up, right? It's saying that the object that you have is not flat, right? That means somebody has actually engraved it, because if I had drawn with a hand, it would have all come into focus. But because there's an engraving, there's a depth variation, and that depth variation is creating a sense of different degrees of blur, right, as you walk through. Now, this phase is what I showed there. Okay, so this portion was cropped. Okay, and the idea is that can you kind of use information like this to be able to say, right, what is the object shape. Okay. Oh, close this. Okay, now let me go back there. So now maybe you can relate. Right? Now you have to relate. Okay. Now this is that face, and this is the depth map. Now this depth map may not be so great to appreciate, but I have others. Okay. But the catch is this, right? Think of it. I mean, if you can't do stereo on this, first of all, it's such a shiny surface. Correct. I mean, even to find out where every point is going is so hard. and then you need a depth map that should be dense, because if it just give you a few points, right, you can't even make out that it's a face. And thirdly, right, you may not even be able to do stereo because you need a baseline and the object itself is so small. Of course, there are stereo microscopes, but the idea is that, right, can you do using something else? And after all, a microscope comes with a depth of field that is only in terms of microns. It comes with that. It's not like you have to make an extra effort. It comes with that kind of a depth of field, and therefore, right, you might want to say, okay, this lens formation, I know how the images are formed. Now, can I right, use that as a cue to now extract my, like I say, depth out? Okay. Now, let me just quickly go through just one sort of a derivation for stereo, right? Before I so I'll start with simply a pinhole model. Okay. So what is the typical idea that one uses in a stereo? Okay. So let's kind of look at stereo now. Okay. How does stereo work? So why is it that, right? Why is it that if you do a correspondence matching, you get a sense for depth? Okay. So the way to understand this is to sort of imagine that let's say, right, you have a point, okay, in the scene. Let's say I have a lens. No, not a lens. I have really a pinhole. Okay, and this ray, it travels through the aperture and then hits my image plane somewhere here. Okay, and this is my focal length f. Okay, this is really a pinhole. Okay, stereo is typically for pinhole. You can also do stereo if it's a real aperture. Okay, nothing stops you. But normal stereo algorithms are all assuming a pinhole. Okay, so here is a point P. Okay, and let me say that okay, and this, of course, is your optical axis. This is the aperture. This is that pinhole. Okay. Now, if you say that, right, I mean, I know this point here, and then I want to find out where is P, right? I can keep traversing on this ray, but then I don't know where to stop, right? Because the point could have been here, and I could have still got an intensity there. The point could have been here. I still could have got an intensity there. So any point on this ray is equally valid, right? I don't know where to go back and stop. So in stereo, right, what is normally done is you translate the camera now. So you're here. So here is your pinhole. Okay, now you translate. Let's say, right, you come down like that, and then you take right, one more. Okay, now let me draw an optical axis here. Okay. And then you take a second image, okay, which basically means that earlier, right, you had a point. So the image of this point in the first image appeared here. Now you kind of say translated, and this is called a baseline shift. Okay, so the way stereo typically works is you don't bring it forward and all. It's simply you just translate in plane. You go like X, you go like X or you go like Y. Typically it's X. You don't do X and Y and all. You don't gain anything great by that. So you will simply do, let's say, an X shift. Okay, so that's what I mean by shifting it down. Okay, just along this X direction. So now if you were to tell a few things, let's say from here to here is your depth, and that, let's say, is Z. Okay, and let's say the initial origin, let's assume it's here. Okay, with respect to the first camera center, let's say that is my origin. And let's say this P has coordinates, let's say X. Okay, so X would be this. So this is X. So X and Z. Okay, with respect to this camera center. And then I have moved by an amount, let's say B. Okay, that's a baseline shift. I moved this camera by B. I've come down here, and then I see this point here. Now, suppose I assume that, right, there is a shift or something that tells me exactly that this point has gone here. Correct. Now, the same point, right, I can also draw here. Okay, instead of looking at the inverted thing, I can say that this is my XL, okay, which is my image coordinate in the first. It's called a left-right pair typically. Left-right. Okay, so that's why I write XL and XR. So left-right. So this point, so right, this is XL. Okay, I'm just marking it on the other side. And similarly, right, this is your XR. Okay, from here to here. So which means that I have to go exactly one focal length away here somewhere. Okay, and let's say, right, I have something like XR. Okay, so from here to here is exactly F. All right, because I'm just marking it on the other side. So here to here, this is also F. Now, if I simply use similarity of triangles, right? So what I see is, with respect to the first one, I see that XL by F, right, is equal to So, where is this XL? So, right, so I am looking at this angle, right. So, that is the same as, so this is the origin, right. So, x by z, or in other words XL is fx by z, right. This is something that we know, this is a perspective projection, we know this. Now, look at this other one, right. If I look at this angle, right, now what I have is xr by f again, right, because from here to here is exactly f. So, xr by f is equal to, now from here to so from here to here it is actually x plus b, right, because I have translated further down by b. So, it is like x plus b by, okay, z is from here to here. Okay, I wrote it a little wrongly, from here to, z is from here to here. Okay, I think I wrote it from there to till the image plane. Okay, not from the image plane, you know that it is from the aperture. Okay, z is there. So you have x plus b by z. Therefore, xr is fx by z plus fb by z. Therefore, if you compute a disparity, which is xr minus xl, okay, a disparity is the shift. Okay, so this is called a disparity. So, which means that this is the amount by which this pixel has shifted, right, when you shifted the camera. So, on the image plane, how much has it shifted? It shifted by xr minus xl, and that, as you can see, is simply fb by z. Or in other words, I can compute z to be fb by xr minus xl. So, it is like saying that now, see, now that I have a second ray, right, if I do a triangulation, earlier I went on this ray, I did not know where to stop. Now, I have one more point, and that is the same pixel, right, that is the same point that is appearing here. So, if I now go back, right, so where these two rays intersect is where that P is, right. In effect, triangulation is what you are doing. But in terms of just simple equations, it turns out that if you know f precisely, if you know the baseline shift, that means if you are actually if you know how much you shifted, and if you can compute a disparity, which will have to come through SIFT or something, which is again hopefully robust, then you know that, right, you can actually compute z. Okay, which basically means that if you can do this for every point in the image, for every point you can find out where it has gone, compute this disparity, then you know that you compute the whole z. Okay, but then it's not that easy, because there will be errors and so on, because your this one correspondence could go wrong, or image may not have say this one a texture in some places. Things will go wrong, a little bit here and there, but then overall, right, people know that, okay, there is this information there which can be tapped. Okay, so this is how stereo works, but here you have to actually move the camera. Okay, we will look at the other one when we meet on whatever, right, next class.